Okay, well, thank you very much for having me today. It is my pleasure to share with you some knowledge about the analysis of slag, and I will talk about this. So just briefly about myself, I'm an analytical chemist. I studied analytical chemistry and I worked for many years in industry. I have a lot of experience as a research and senior research chemist. Specifically in the cement industry. I now work for Rigaku, which is a Japanese company in Europe, in Germany, where we do feasibility studies of new materials, application setup, we do training, we do technical support. So I would love to show you who Rigaku is. As I mentioned, we are a Japanese company. We were founded in 1951. As a family-owned business, we started off like this, but now we've grown into a global industrial company globally, where we have a lot of innovations in crystallography, diffraction and fluorescence, all related to X-rays, right? I will talk about wavelength dispersive X-ray fluorescence, which is the main analytical instrument used for material analysis. Yeah, we have the philosophy of Kaizen because we are a Japanese company for continuous improvement. So you can see here we have a timeline which shows the continuous development and improvement of our products. So at the bottom here you can see our laboratory in Germany. At the top, you can see our factory in Japan. So yes, in everything we do at Rigaku, we believe in advancing humanity through science and technology. And the way we advance science and technology is by making our instruments exceptionally well engineered, user-friendly, and we offer the best service, of course. And therefore, we have established ourselves as a global leader in all analytical X-ray solutions. So this is, once again, just showing you how we get involved with our customers in our laboratory based at the Center of Excellence in Europe, in Germany. Okay, so let me briefly tell you what X-ray fluorescence is. It's basically an instrument where we can determine the types of elements, either qualitatively or with a quantitative analysis. So we can either use semi-quant or calibration methods. So at the top here, I don't know if we have a pointer here, but I can try to get it. No, I don't have a pointer now. But anyway, yes, you can see this. So here we can see we have an X-ray source which bombards our specimen with primary X-rays, and basically we get the fluorescent X-rays, which then go through a collimation system, basically onto an analyzing crystal. And this is why we call it a wavelength dispersive instrument, because this analyzing crystal has the function of separating our characteristic nickel, iron, and chrome K-alpha lines, which are then detected by our different detectors. So based on the intensity that we get, we will have a direct relationship with the concentration. So as I mentioned, we can do qualitative or quantitative analysis. So here we can see the difference between the hardware configuration of a WDXRF and an energy dispersive XRF. So here you can see we have different setup. Elemental range is completely different to energy dispersive. Here we have smaller instruments, more benchtop, more used for screening, compact design, but yeah, as I said, more for screening analysis. Not very accurate and not very precise. But if we look at our WDXRF, we have larger instruments, a better hardware design, bigger analytical range, and therefore we have a higher resolution and a higher sensitivity, especially, for example, light elements. So this is really suitable for extremely accurate and extremely high precision analysis. So this is our product portfolio. You can see we have the floor standing instruments. They are all called ZSX, meaning atomic spectrometer for X-rays, and we have the Primus series, so Primus 3, Primus 4, Primus 4i. Due to time, I do not have enough time to explain the hardware parts, but the best part is that Rigaku have thought about the best analytical design for your analysis of all kinds of materials. So meaning we have a geometry above the sample and geometry below the sample. Smaller footprint, larger footprint, normal sample throughput, higher sample throughput. Some are designed for liquid analysis, some are designed dedicated just for liquids, so very high throughput here for liquids. But if you have solid samples for industry, then of course we would go for example Primus 4, because this offers the best technology for you for the analysis of those very complicated matrices. Then we have the benchtop unit, almost like a backup system, but it has its different purpose, right? And then the high-end instrument with a much smaller footprint, but designed for very, very fast industrial analysis of different solids and so on, samples. Yes, so today I will talk about slag. So slag and how we do the analysis using WDXRF. So my presentation will involve the fusion method because it is a reference method. We will look at the compliance according to the international standard. We will look at the analytical method that's been developed and what are the advantages of an XRF spectrometer in terms of validation, verification, and of course the maintaining of the instrument calibration. So this is one of the biggest advantages of X-ray fluorescence because we can create this calibration method, keep it on our instrument by basically maintaining this calibration, followed by a summary. Okay, so let's look at how we can set up our spectrometer. So not only do we have a spectrometer, but we also need to have calibration standards. So here we can see an example of a package that's available that we can prepare as a fused bead, which is basically the equipment that you see here. So let's look about the sample preparation part. So of course, fusion involves the process of melting a solid sample, which is a powder, into a molten glass, yes? So if you look at the process, it involves an oxidation step where we get rid of our volatile components like CO2, oxygens, and nitrous oxides, and all kinds of oxidation changes that happen within the material at a certain temperature for a certain period of time. The next step involves the melting of this oxidized sample or pre-treated sample into a flux. And then the dissolution of this by introducing steps like the mixing and the cooling and the casting, which then takes place, as you can see per the diagram here. So the cooling part and the casting part is also an important part of this preparation of the sample. Because if we don't cool in the correct way, we don't mix in the right way, we don't cast in the right way, we can cause crystallization and cracking. So what is the advantages of fusion in a nutshell? It's very quick and easy to explain because I think we've pressed for time. If you have more questions, I can explain it in more detail. But here you can see an example of a calibration where we have pressed powder. So the problem with pressed powder is the matrix. So if you look at calcium, it can exist as calcium oxide, calcium carbonate, calcium fluoride. So they are all calcium. We want to measure calcium, but unfortunately they exist in different matrices. So that means if you measure a sample by XRF with pressed powder, we will have different calibration curves. So to take away the effect of matrix and particle size that is related to pressed powder, we can create the fuse bead calibration. And this means now basically the calcium, all the calcium matrices fit onto one calibration curve. So this is the biggest advantage here. So we take away the error related to particle size. We take away the error related to the matrix and the mineralogy. Okay, it's also an example of we can create this calibration not only with certified standards, but also with synthetically made calibration standards. So we can spike samples and create our own range that would be suitable for the quantification. So here you can see the example of how we would do a pre-treatment of slag. Why do we need to pre-treat the slag? So slag has the nature that they could be existing in a glassy form or in not an oxidic form, but more a metallic form. So if we directly fuse the slag with platinum, so here you can see an example of a platinum mold, you will then suffer from damaging your platinum because it forms a eutectic mixture with the platinum and it can degrade the platinum, causing pits and so on. So therefore we have to introduce an oxidizing agent. So the oxidizing agent in this case is called strontium nitrate. So we pre-treat the sample in this way, but we use now not platinum crucibles, but we use like these alumina crucibles that can be subjected to the very high temperatures of around about 800 degrees. So this is the kind of program that we would need to follow. And then after the oxidation treatment, we can then follow with the main fusion, which takes place as stated here. And then, of course, the pouring and the cooling. So let's look at the uses of slag. So slag can be used in the cement industry to extend the cement. So this means we can produce cement in a greener way. So it means we can produce less clinker and use it with more dilution by adding certain components. So here you can see a uniform conformity from the international standard, the European norm. And here you can see how we can extend the cement with different kinds of materials. So the material that I'm going to look at is called the CEM1, CEM2, CEM3, and CEM4, which is like a composite cement. And here you can see that we can use this blast furnace slag to extend the cement. So this is a way of producing a greener cement by producing less clinker. So cement can be extended in the following ways. We get different categories for CEM2, different categories for CEM3, and different categories for CEM5. So you can see the extension that can be added. But in order to add this blast furnace slag, we need to make sure that it conforms to the conformity, right? Because if it does not conform to the conformity, we will not be able to use it in the extension of our cement. So it's very, very important and very critical that we accurately and precisely measure the slag before we make these blended cements or extended cements with the slag. So let's look at slag. How do we do the conformity testing of slag? Well, the chemical composition of ground granulated blast furnace slag is given here. So according to this international norm, we need to categorize and make sure the analysis of slag conforms to this composition that is stated in the international standard. So in the international standard, they say the ground granulated blast furnace slag to be used in concrete mortar and grout should consist of at least 2/3 of calcium, magnesium, and silicon dioxide. And a third should be as alumina oxide and the other minor elements that could be present in that particular slag. And most importantly, the ratio of calcium and magnesium over the silica should be greater than 1. And then if it follows this diagram that you see here in terms of composition, it can then be used in producing our extended cement. Once again, just showing you and re-emphasizing the percentage of slag that can be added to the clinker to produce the same 2, 3, and 5, as I have explained. So how are we going to test the slag? Well, Rigaku sell X-ray fluorescence equipment, and this is the analytical method that can be used to measure accurately and precisely the ground granulated blast furnace slag. So in this example, I showed you our smaller instrument. Of course, the bigger instrument, if you are interested, you can contact us. You can see that we have a Super Mini, which has a small sample changer of approximately 10 positions, and you can fit different sizes in here. So how do we perform the analytical method? Well, as I explained, we need a calibration. And in order to create a calibration, we can get calibration standards with a suitable range so that we can cover 95% of the natural distribution range to accurately and precisely measure the ground granulated blast furnace slag. The standards that we use need to have the correct concentration, otherwise we will not have an accurate and precise determination. So, as I mentioned, the fusion is the best for accuracy. We take away the error from particle size and matrix. We get a very homogeneous mixture, and we ensure that the thickness of the fused bead depends on the sample and flux amount, and the shape of the analytical mold will determine the analytical surface that we will measure. So here you can see an example of some fused beads, which are glass matrix. Yeah. What about the calibration? So our software is very nice because we can create the 27 standards as fused beads. We create. Yeah. Okay. Yeah. But it's not fair that other people speak for longer than they're supposed to. But sure, yes. 27 standards are used and 5 validation standards are used to validate the method. This is the example of the range of the calibration. So as you can see, the Super Mini is quite easy because we have the hardware configuration that you can see here that will be used to set up the method. So of course, as you can see, we have excellent light element determination for elements like sodium, which are very difficult in X-ray fluorescence, magnesium and chloride, as compared to smaller kind of units. Yeah. So if you look at this diagram at the bottom here, you will see the spectral energy profile here for energy dispersive instrument where we cannot pick up chlorine, but with our Rigaku Super Mini, we can pick up even 300 parts per million of chlorine in a very difficult matrix. Yeah. So this is the example of a calibration where we created the 27 standards. This is a snapshot of alumina. We have a drop-down list here with all the elements, and with each calibration, you can see accuracy, you can see the intensities, you can also see the calculated and standard values with the deviation. With each calibration, you will get the regression coefficients and the equation. So, you know, the intercept and the slope. So this is very useful. And here's a summary of the regression. So you can see very, very pleasing and excellent regression with very good accuracy for all the oxides that we would like to measure in the slag. Well, one of the biggest advantages with X-ray fluorescence is that you spend a lot of time to create these perfect calibrations, but now we can compensate for the intensity change by using a drift correction. So this is like a method that's used in X-ray fluorescence to ensure that we can update our spectrometer with the change of intensity. So we can use the calibration for a long period of time. What about validation? This is a process of basically proving that your analytical method is fit for purpose. So how do we do this? We do this by creating certified standards that are independent of your calibration method, and then comparing this to the certificate of analysis to assess if the uncertainty of method is provided is correct from the certificate. Yes? So here you can see the example. If you have time, you can go through it because I don't have enough time to explain it. So I will just skip it. Verification is ensuring that we produce good quality data and that it meets the quality standard according to the international standard. So here you can see the example of this verification. And yes, the continuous assessment should be done in the following way, by including check samples, by including the check on the analysts, by including the check on the calibration, preparing a secondary standard which can undergo the same process of preparation in a laboratory. With our instrument, we get control charts to ensure that we are producing consistent results with a good preparation and a good working spectrometer. So, in summary and in conclusion, the Rigaku XRF, WDXRF instruments are very easy to set up. This is just an example of a very small benchtop unit. But of course, we get more powerful results from, of course, our floor standing instruments. So these kind of instruments are used for process optimizations, the analysis of all kinds of solids and liquids. But I just spoke about analysis of blast furnace slag, where we can optimize, for example, the slag to clinker ratio, to produce the international cements, extended cements like CEM2, CEM3, and CEM5, which is the composite cement. So, in conclusion, we can, as Rigaku, provide good preparation solutions, an excellent calibrated system. We offer the tools to verify and validate and continuously ensure quality control and the maintenance of your calibration. So yes, in this solution I showed you an example of application packages together with technical support and of course the instruments. So most importantly, the method development and the training and the feasibility studies need to be accompanied with these very complicated instruments, yes? Because you need to learn XRF. It's not just that you use it, no, it needs to be taught. So thank you very much for your time. And if you have any questions, we have some brochures at the back on these beautiful instruments that can help you to measure all kinds of materials, any kind of matrix, polymers, solids, metals, liquids, any powders, whatever you want to measure. Everything in this building is measured by XRF.